Okay, welcome back everybody, good morning. So today our topic is going to be the third type of differential equation that we are talking about in the last one, hyperbolic equations. But before going there, I got a few questions about the eigenvalue problem yesterday, and especially about what is wrong with the high eigenvalues and high eigenmodes. And so I wanted to show a little bit about this first. So let me comment this one here out. So unfortunately, I seem to have messed up overnight and have erased my nice little eigenvalue problem code that I had myself that I showed you yesterday. So I just frantically tried to put it back into order. Yes. And so this little piece of code here is basically the same we talked about yesterday. We are starting with Chebyshev matrices. We set up the eigenvalue problem that is actually remarkably simple in the code, even if it is really difficult or moderately difficult to figure out why this is the right thing to do. And then here's all this post-processing step that I don't want to get into to get the results look more uniform to each other. And if I'm solving with 7 points and I'm solving for the fundamental mode, this is already quite recognizable as a sine wave, or 1/2 of a sine wave. And if I increase resolution by adding more grid points, then this is even more recognizable as a sine wave. And it also is more and more, it also is even more accurate than this plot suggests, because here again, MATLAB simply connects the individual grid points. But if I were to interpolate with the Fourier series, even the 7-point stencil would look very, very good. So now the difficulty is that the higher order modes, as I've said yesterday, have more and more nodes. And I'm soon showing you the 10th overmode on the right-hand side. And this 10th overmode will have 10 zeros. So it will be looking something like this, except this is the 1, 2, 3, 4, 5, 6, 7th overmode, but it doesn't matter. The point is, there's a lot of fine structure here. And if you're trying to resolve all that fine structure, you need an appropriate number of, excuse me, of basis functions to do so. So if I'm starting with n basis functions, I'm getting out n minus 2 eigenvectors, because we have been cutting away the first and the last column of our matrix. And so the n over 2th correct eigenvector would have, let me count this has 0, would have n minus 3 zeros, and correspondingly n minus 2 half periods. However, I only have n basis functions with which I can go up to e to the I n over 2x. So I can't represent all these high frequency content. Well, actually, this would be correct for a Fourier series. Let me remove this again. But the similarly is true for Chebyshev, because the Chebyshev polynomials cannot really resolve as many periods as you have grid points, because then you don't have any resolution within any period. If I'm trying to do this, and if I get this right, which so far I have not, because I've commented this out, this is what the naive Chebyshev, the eigenvalue calculation returns for the 11th eigenvector of an n equals 13 expansion. So this should have 12 or 13 oscillations, and as you can see, it has all but. It's completely different looking from the actual eigenvalue, eigenmode. And because my underlying series cannot represent the shape for the eigenmode, it will also not be able to reproduce the correct eigenvalue. And so a rough rule of thumb is that as soon as you have approximately twice as many basis functions, then you can resolve a certain mode, or if you divide the statement by 2, the lower half of the eigenmodes and eigenvalues are usually trustworthy. But precisely how many are trustworthy, you can only find out by solving at multiple resolutions and checking which ones are the same. For instance, if I now go up and add a 31-point solution to this, then you can see this begins to look quite oscillatory, as you would expect. It still is quite jagged because I'm not yet interpolating. Let me try to interpolate as well. This is almost certainly going to fail, but I'm ambitious. X fine equals np dot linspace to pi 500. How did I call the interpolation function? Chebyshev interpolate Evex of 10, comma 2 spec, comma x fine, and this is fine. X1 dot plot x fine, comma nothing. Okay, obviously I got it wrong. That actually wasn't too bad. My next problem is that I got my interval wrong, -1, 1. And now we're actually having it here. And now I can get really fancy and plot only symbols for the Chebyshev collocation points, and I even mess up plotting symbols. I really am not particularly awake this morning just yet, it seems. Okay, so now we've got it. So if you're trying to look for the 10th eigenvector with only 13 Chebyshev points, you get these blue symbols and the interpolating polynomial, which looks not at all like a sine wave with 10 zeros. But as you increase the resolution enough, you get to this red curve, which now looks very, very close to the sine wave with 10 cycles. I'm explaining this here for the good old oscillating string, but if you have any other eigenmode problem, the same general structure is true, that with each higher eigenmode, you're picking up one extra zero crossing, and the more zeros you have, the more structure you will have in your solution. The structure may not be as uniformly distributed as a sine wave, but the same storyline applies. Okay. Then let's move on from the eigenvalue problem and move over to the hyperbolic equations. It will turn out that all the spectral business, the spectral discretization, is almost trivial from now on. And we will spend most of our time talking about how to do time stepping and especially how to do boundary conditions if we have boundary conditions. So hyperbolic equations. Bispectral methods. At this point, Geoffrey's and my lectures are actually going fairly parallel to each other. We are both using the same example. I've even tried to adapt to his notation to make life a little bit simpler for you. So wave equation in flat space. d squared of g minus c squared gradient squared of g equals a source term, and g is going to be a function of t and x. So c is the speed with which the waves are going to propagate. Usually we set it to 1, but I left it in so you see where the speed is going to go. And a source, you can have a source term in the equations or not. It doesn't really change any of the math I'm putting at the blackboard, because in the language we had already the last few days, it's the principal part, the highest derivative, that determine the character of the equations. And lower order parts, like the source here, they just don't cause any difficulty in terms of mathematics or numerics. As Geoffrey, I need a first order reduction. So we are going to define two new variables. The first one is called phi I. And this is the gradient of our scalar field. And if I define this thing here, well then, of course, no big surprise. One consequence is if I take another gradient here, I can get out of this that c times the divergence of phi is equal to minus, I'm putting a factor of c here to make all the c's balance out nicely, is equal to c squared times the gradient of g. No big surprise, just putting stuff into each other. The second variable I'm defining is pi as minus the time derivative of g. And if I'm taking this expression here and take a gradient of this equation, I can get out of this that c times the gradient of pi is equal to minus c times di dt g. Let's exchange partial derivative, minus c dt di of g. And di of g we already had, that is phi. So this thing is going to be minus dt of phi. And with these two definitions, I can now write down the scalar wave equation in a form of first order time derivatives of all three of these variables, ddg, dt phi, and dt phi I. So let's see what we have. Let's look at I see a dt phi I sitting down here, so let's take this one first. dt phi I is equal to c times gradient pi, and if I move everything to the left-hand side, then I don't have any minus signs. What else do we have? We have our definition for pi happens to give us the time derivative of g. So this is the first equation here. This is a pi. I have messed up here, haven't I? I need a minus sign. And now we need an equation for pi. Well, pi is the time derivative of g. So dt pi is minus d squared g. So I have these two terms left over, and I can put them in as c times divergence of phi, which I have derived here. And the s shows up on the right-hand side with a minus sign. So this is now the first order representation of the scalar wave equation. Geoffrey explained the same thing yesterday, that's why I went through it quite quickly. And this is now one example of the general form of first order equations. We have a set of variables, u alpha, in this case, g pi I. And we have a set of evolution equations, which here is a little bit simpler than what Geoffrey did. Time derivative of u plus a bunch of matrices multiplying first derivatives of u equals some source. And so these derivative terms here are precisely capturing all the derivatives we have up here. We have here two implicit sums. So the beta is being summed over, and the k is being summed over because of the sum conventions, and to make sure that we have all possible combinations of any type of derivative of any variable is allowed to show up in any other variable's equation. And for the scalar wave, Geoffrey also already went through this. For the scalar wave, this turns out to be that this B matrices, B alpha beta k, are, so they will have entries for psi, pi, and phi I. And they will have columns. Let me see which one is which. They will have columns for dt psi, dt g, dt pi, dt phi j. This one here is a g. I may mess up g's and I may replace g's and with psi's every now and then, because in the past, our convention was to use psi for the variable of the scalar field. And so switching to g is quite new to me. Okay, now let's see whether we can fill this in. In the TTG equation, we don't have any derivatives. So these are all 0. In the dt pi equation, we have one derivative over here, the di phi I. So this is going to show up here in one way or the other as a c delta ki. Because in the kth matrix, only the kth phi I is going to show up. And in the dt phi equation, we have this thing here. And so that should be not here. It should be a c times delta kj over here. This is, if you do this the first 7 times, this is very unintuitive. But what it actually boils down to is that, well, if we do a For instance, if we look at the X matrix, we have still nothing in the top row. We have nothing in the first row. It's a 5 by 5 matrix. We only have one element here in the X phi X component. And we have one element here, this one, and everything else is 0. If I go back to my color coding, I would call this one here C in red, and the other one in yellow. And if I'm doing the other two, the Y alpha beta is also a 5 by 5 matrix. Now the numbers have moved by 1. This one here is still in the second column for pi, but it's now one further down, second to last. And this one in the column for pi is moved one to the right. So it would be over here. And zeros around. And well, for the last one, the Z alpha beta. And I hope, Geoffrey, this agrees with what you did yesterday. I hope we have the same thing. We have the C in the bottommost column, in the right one, and we have zeros down there. I think that's it. So we can represent a wide variety of non-conservative evolution systems in this form. And that's what we're talking about today. Okay, so we have our, I wanted to highlight this here because we are going to first order form. And these matrices BAB, alpha beta, will show up later again in excruciating detail when we are talking about characteristic modes and how to set boundary conditions. The nice thing is we can delay all this pain and suffering of talking about these matrices by first looking at the periodic case with a Fourier series. If we are periodic, we don't have any boundaries, and so we don't have to worry about the boundary conditions just yet. And so in order to get to something nice to show you, and in order to get to a problem for you for this afternoon, let's therefore do the periodic boundary conditions first, and only later talk about the more complicated case. I have my evolution system sitting here. Very good. That means I can erase this part here. And I will be very lazy as well in order to make life for all of us more comprehensible as well. I'm only talking about one-dimensional problem here. So we want to discretize with periodic boundary conditions, which means a Fourier series. I'm specializing to 1D, and to make life even more simple, I'm going back to the usual Fourier interval from 0 to 2 pi. And so the variables I will have left over are going to be G and pi, and only one of the phi's, only the phi x. And because I only have one of them, and I will soon need to put an index here, I, for the grid point, I won't bother writing down the x, so the x is going to be omitted. The idea is now to discretize space, but to keep time still continuous. So our U alpha from t comma x is going to turn over into a U alpha, still a continuous time, but now x becomes discrete, our Fourier collocation points. We call them xj, so let me stick with the j notation. And this is now no big surprise. This is going to be gj as a function of time, I j as a function of time, and I j as a function of time. And this j here is a grid point index. If we were in 3 dimensions and we still had a spatial index at the phi as well, well, then we would have 2 indices and would have to be very careful in not mixing them up with each other. Okay, so now if I do this, my first order evolution system, which originally was g dot equals pi dot equals minus c phi prime, phi dot equals minus c pi prime. Yeah, I can keep on putting the s in or not. It doesn't really make a difference. I probably will forget writing the s sooner or later. It doesn't change any of the steps I'm going through here. What used to be the partial differential equations they now turn into a discretized form. So the first one, if I evaluate this at the grid points, I get very simply g dot I as a function of t equals pi as a function of t, pi j, gj. It's just this thing at the grid points, index j attached. For the next one, well, we have a pi j of t first time derivative on the left-hand side equals a derivative. So here we throw in our differentiation matrices, djk phi k as a function of time. And if we have an s, there's an s j of time here as well. And for the last equation, for the phi dot equation, that's phi dot at grid point j, which is a function of time. This is going to be minus c times differentiation matrix jk times pi k as a function of time. So we have a nice little set of equations here, which weren't particularly painful to arrive at because we already did all the work in explaining and working through the differentiation matrices. Let me pause at this point and offer you the opportunity of asking questions. Thank you very much. This is very possible. And you're completely correct. I have, as always, very easily overlooked minus signs. So we need two minus signs here.
The P matrix looks symmetric.
Yes.
So is that the symmetric hyperbolic?
Excellent question. So indeed, in this particular case, these matrices are symmetric. And this is very good. It leads to nice properties of this set of partial differential equations. Yes, indeed, this is precisely why this type of system is called symmetric hyperbolic. We'll get to this later after we've had some fun with the Fourier series. Okay, let's move on. This set of equations here that we have discretized in time has now a finite number of degrees of freedom, namely 3 times n real numbers. Three for g, pi, and phi, and n the number of grid points. And so what we have is we now have here equations that tell us on the left-hand side the time derivatives of each of these 3 times n numbers as some combination of all these numbers itself. So this is now an ordinary set of differential equations. For, how did I write this? U alpha I, or just U alpha, or just U. And so we have an equation du dt is some function, which is also a vector function f, operating on all these u's themselves. Inside this u vector, we have n points corresponding to the g's. We have n points corresponding to the pi's. We have n points corresponding to the phi's. And all these are mixed up in the f on the right-hand side according to these equations here, including these derivative matrices. But overall, what this is a set of ordinary differential equations for 3n unknowns. And so after discretizing space, throwing in these differentiation matrices, this is all we've done. We have our method of line ordinary differential equations that we now need to solve forward in time. By the way, if you had done this with finite difference methods, for instance, this whole setup here on the left-hand side would be utterly identical. And the only difference, if you had done finite differences, is that here, for these derivatives, you would have put in your finite difference stencils. And in some sense, all the spectral methods we are doing in this type of formulation that I'm presenting here boils down, surprisingly enough, by replacing your finite difference stencils by something smarter. And if you have Chebyshev series, instead of doing a uniform grid, also using smarter grid points as well, plus the smarter differentiation matrices. Okay, we have ordinary differential equations.
The pink C should play one row up.
In which one? Yes, you're absolutely right. I'm either going too slow or too fast here if you have time to still think about these matrices. Thank you. But yes, this is in the second row because this is the row that corresponds to pi. Pi is a scalar variable that only has one row. So all the red C delta kj's, they all have to be in the second row. Okay, let's talk about, unless there's another question. let's talk about how to do time stepping. I'll continue my philosophy of really explaining everything and not using any preconceived tools. So I'm also giving you a really brief intro to time steppers. So our goal now is to solve this with a time stepper. With ODE time stepper. And the quickest one you can write down, and the one you will never use again afterwards, is forward Euler. So we're writing our unknowns at time tk as u cap uppercase K, and tk is just delta t times k. So we're doing uniform time steps. As k becomes larger, we're moving forward by delta t's. And the forward Euler formula is that u at the new time is the same as u at the old time, well, plus its time derivative times delta t times its time derivative, f of t comma uk. So this f function can depend, in our case, the f function only depends on u, but it can be also depend on time. For instance, if the source term here would depend on time, then this would show up here in the f function as well. And so if you wanted to visualize this, you can make the following type of diagram here. On the x-axis is time in units of delta t. So we're probably starting at 0. At some point we are reaching k. And where we want to get is k plus 1. And on the y-axis is the function u itself, or well, at least one dimension of u, because more doesn't fit on the two-dimensional blackboard. And so at uk, you have a certain value here, and this would be uk. And now the f is the time derivative of u. So the f tells us what the slope is. When I'm evaluating at this point uk, f of uk, t comma uk, dk comma uk. Now forward Euler is very trivial. I'm going from k to k plus 1, just proportional to the slope. I'm simply going along the slope all the way up here until I have uk plus 1. So let's think about, so all of this is very intuitive, and I hope quite comprehensible. But with the utmost simplicity here, what we're giving up is actually accuracy. We are only doing the time step to first order in delta t. So what we're actually missing here is the second order in t contribution. So in each time step, we are going to end up with an error that is going to be order delta t squared. If I now want to evolve to some finite time, I need a number of time steps that grows like 1 over delta t. So I'm making my time step smaller. I'm accumulating less error per time step because this goes down, but I'm losing some of this already because I need to take more time steps. So the error to time t which needs t over delta t time steps, because the number of time steps grows like 1 over delta t, the error is only going to be the 1 delta t that's left over. And this is the reason why nobody in reality actually uses forward Euler, because it is very, very slowly convergent. And this is called convergent to first order in T. Nevertheless, let's bring this up and let's show you how all of this looks in practice. I hope I haven't removed that part of my solution as well. I think this is demo 7. Okay, yes. Actually, let's go through this and then talk about it afterwards. So here's demo 7. Let me first explain this one here. I have defined a few pulse shapes here, a wide pulse periodic, a wide pulse non-periodic. So the periodic one is my exponential of the cosine. The non-periodic one is just a Gaussian, e to the minus x squared, with some width p in front of it. And I also have the same things in sharp, a sharp pulse, which is again e to the cosine, but now this number in front of it is larger. And the sharp pulse non-periodic is a Gaussian, but now with a larger coefficient in front of it. These functions turn out to be quite useful when I'm setting initial data in a little while. So here is the function for instance, for the wide pulse periodic. It's actually not particularly wide already, because I wanted to show something that is where you can see it nicely moving left or right. And let me also put on the other one, the sharp pulse periodic. And now it has disappeared. It's basically the functions from the first or second tutorials. It is a pulse that is more condensed along the x-axis. Therefore, it will need a few more Chebyshev Fourier modes to resolve, but all of this is still nice enough that we can easily resolve it with a few tensor Fourier functions. These pulses also return the first and second spatial derivatives of the shape themselves. So if I'm going back to the white one, and I can also put in and plot the first and second derivative. And so, well, the first derivative of the blue function is the orange one, and the derivative of the orange function is the dotted curve. No big surprise here. These functions will turn out useful in a very short period of time. Okay, now let's see how this whole thing actually looks like in terms of code. And we are still in a situation where the code is so short that the comments tend to be longer than the actual code. This is a function that's going to do the right-hand side of our equations. It takes u, our variables. And so what we are doing is we are splitting them up into g, pi, and phi, simply because it's easier to code equation in terms of comprehensible variable names rather than indices. And now here I have the g dot equals minus pi, the pi dot equals minus derivative of phi, and the phi dot minus derivative of pi. This is using not the matrix multiplication, but it's using the functions that are doing the FFT and multiplying by IK and doing an inverse FFT. But it's the same story. It evaluates this derivative term here at the grid points. And again, everything here are numpy arrays. So this g dot equals minus pi, it sets the conditions for every single one of our n grid points immediately, all at once. Okay, we need some output memory space into which to put the time derivatives. I'm just copying the input variables. That is a trick to get around having to worry about how to set up a numpy array of the correct size. And then I'm assigning back g dot, pi dot, and phi dot into the 0, 1, and 2. And I return it. So this way, I can use this piece of code with time steppers that only know about U and that don't know about the internal pieces of the partial differential equations we want to solve. And the time stepper that goes along to it, well, somewhere I have a forward Euler, if I just find it. Here it is. One step of forward Euler. It again takes the current variables U. It takes a function that evaluates the right-hand side, and it takes a TT. And so in this case, the comment is ridiculously much longer than the actual work. U at the next time step is equal to the current U plus delta T times the function f of U. So this is literally just coding this thing here as is. And because I have outsourced the f calculation into its own function, the Euler time stepper code is so short and so concise. Okay, so now we can do one time step. That's not enough, we need to do many. So somewhere I also have a function that takes a time stepper and a right-hand side, a current time, and the time to which we want to go to. And so what it does internally, it first figures out what time step to use. It turns the time step into a number of steps. And then it adjusts the time step a tiny little bit, such that after this integer number of steps, we are exactly at the asked for final time. If you don't do this, well, then you are getting close to the final time, but you might be a quarter of a time step too far, or a tenth of a time step too short. And so you'll never precisely make that time. And if I now very soon are going off and trying to compare solutions that we are computing with different time steps, if you now end up comparing the solution done with time step 1 at a time of 5.001, and you're trying to compare this to the solution of time step 2 at a different time, let's say time equals 4.9998, then you'll see that you have a problem in that you will have differences because you're using a different time step, which we want to figure out how big the time step error is. But all of this will be meshed in with the fact that we have ever so slightly different times. And well, the solution changes between this time and that time. And if you don't account for this, you're getting out wrong results. So tiny little time stepper, and then all of this is being put together in something like this here. I'm not quite sure about the setup functions. I think they are fairly convenient, but also not that useful. So what they do is, the setup functions that I'm using here, they set up all the information one might need. So here is are the x coordinates. And what I'm doing here is I'm making what's called a named tuple in Python. And inside this named tuple, I'm going to put the minimum grid spacing and the grid points, because those tend to be two very useful pieces of information that I'm going to need throughout the calculation. So I'm putting this extra information into the info variable. You might have seen the info floating by in the previous slides as well. I'll highlight it when I get to it again. Then we need to decide on what we are using for initial data. I'm having the option here of specifying a profile, and I'm getting the function and its first derivative from one of my profile functions. And then I'm setting G to be the profile. I'm setting phi is the derivative of G, to be the derivative of the profile. And pi is something interesting we need to talk about in a little while. Let's just leave it as is. I'm also setting pi, the time derivative, to the spatial gradient of the profile. Then we need to pack our variables into one overall structure. So I'm making a NumPy array with 3 entries first for our 3 variables and n grid points, and I'm filling it on the next line. And I'm returning the time we're currently at, the current u, and this info that is useful for other things. Just to highlight a Python idiosyncrasy and how this packing and unpacking works. So here I have a little example. Yes? Initial time. I have a little NumPy array just to make sure I know what's going on. If I print it, you get, well, all zeros. If I'm taking out the 3 variables A, B, and C, U0, U1, U2, I can now go on and modify them. This is what we want to do. But now so far everything does exactly what you think it is doing. But now comes in the last line the perhaps surprising thing. We have modified the A and C variables. I'm printing U, and nevertheless, in U now suddenly, the 2 and the -33 show up that I put into the A and the C. The problem here is, or the cause for this is that Python by default uses pointers. So if you initialize A as pointing to something in U, it's not copying the data in U, it just has A pointing to the same memory location. And therefore, if you really want a new set of data where you can modify the numbers independently, you actually need to explicitly copy the data, as I have done, for instance, somewhere up there in my right-hand side function, I believe, here. So this really makes new data. And now I can go on and actually modify the new data without modifying anything else and accidentally messing up the U variables I also carry around. Okay, I've gone through this probably a little bit faster than for you to pick up every single line of code here. I hope the gist of this has gotten across. And the tutorial is going to be to precisely reproduce this yourself this afternoon. Let me show you what now comes out of this. I'm setting a certain resolution, 32 grid points. I haven't yet talked about the Courant factor, so this is basically the time step. We'll talk about this once I'm done here. I'm using a wide profile. I'm using currently the forward Euler time stepper that I just showed you. And now what happens, I'm setting up my initial data with n grid points and the profile I just spelled out in line 8. I'm plotting the initial G, always a good thing to do. I have no idea what these two lines do because they are irrelevant. And I am also collecting G at specific times in this G out list in order to plot it afterwards. So I'm going 4 times, evolving each time by 1 extra. The time stepper evolve will take as many time steps as it thinks it needs. And then after I've evolved from 0 to 1 to 2 to 3 to 4, I'm extracting variables and collecting G in the output. I'm doing nothing with the C, so let me comment it out. And I'm also plotting P. So let's see how this looks like. And let's first do this in a very simple way. So here is the solution at time equals 0, our pulse. And at time equal 1, it has moved to the right and is now sitting at, instead of at 3 point something, at 4 point something. So it has moved roughly 1 unit to the right, as it should, because I have set C equals to 1, so all the speeds should be 1. If I keep going and to all my 5 cycles that I had in my little loop, the initial data moves right, runs into 2 pi. And because everything is periodic, it now shows up on the left-hand side and it keeps going. Question here. If I'm looking at my initial profile pulse here and the one I have here towards the end, do you recognize a difference between the purple and the blue one? I see quite a lot of people nodding and making symbols with their hands. Yes, I think the purple one is getting sharper. And the other thing, at least to my eye, is that the purple one is getting too big. And before fixing this, let me first actually turn on the lower panel, where I'm going to plot the difference between the solution and the actual correct solution. So I happen to know that the exact solution is the profile evaluated at position x minus t for a reason I'm going to explain to you in a little while. And here, for instance, you're now seeing why this info function can be useful, because it stores the grid points and I can easily get them back whenever I need it. So let's plot in the lower panel the errors. And so first of all, the scale is smaller than the top panel. This is certainly good news. But as you can see that at time equals 1, the error is still quite small. Time equals 2, it gets bigger, and it's up to 0.25 or so at the end. That's not that surprising, because as the title says, I'm using here a remarkably large time step. If I'm now turning my time step down by a factor of 10, then what is an error of order 0.2, if I have not made any errors, should go down to an order 0.02. So I'm using a 10 times smaller time step. And so this thing here comes in and makes the error 10 times smaller. Of course, 0.02 is still nothing really to write home about. I've told you, hey, spectral methods, you get 10 to the minus 10 accuracy. So let's go further. Let's put down another factor of 10. And now the 0.02 turns into a 0.002. So we are getting ever closer. And if you now look at the top panel, now the purple shape actually is hard, or is impossible to distinguish from the blue shape, because it's actually identical to 0.2%. It has the same width, it has the same height, it's just the same thing, at least within the line thickness. But we're still by far not down to 10 to the minus 8 or anything of these astonishing high accuracies that I have been promising and advertising to you. So let's put in another factor of 10. And this time around, we are getting to 0.0002. So we're certainly getting there. Let's put in another factor of 10. And yeah. And at some point, you realize that this forward Euler first order and time stepping just needs so ridiculously many time steps that, yes, we have our absolutely stunningly great spectral expansion in space that give us infinite resolution for basically no work. But if we now have to do infinitely many time steps, I'm exaggerating a little bit, then we're not really getting anywhere. And so this forward Euler method, because of that reason, because it's so slowly convergent, is not used for any practical work at all. But if we are willing to wait, we actually have gained another factor of 10, and we're now down at 10 to the minus 5. So there's one more thing I wanted to point out here. Let me get back to a more reasonable Courant factor, so this actually runs quickly. And let me also get back to our initial data, where I had put down that the initial conditions for pi is just the radial shape of the profile, the gradient of the profile itself. Let me put a minus sign here. And let's go down to the plot that we want to have. And now the plot looks like this. So our t equals 0 curve is identical to before. But now t equals 1 and t equals 2 is moving to the left instead of moving to the right. And so what I've done here with these initial conditions is I've figured out precisely the right choices of pi's and phi's and g's that correspond to a purely left-moving and a purely right-moving pulse. Okay, so let's switch back to the blackboard. Yes?
You obtained by subtracting from the exact solution.
Oh, the errors now are wrong. Good catch. Because I was doing the errors by hand, and I haven't yet switched over from the right moving pulse to the left moving pulse. If I put the plus sign here as well into my profile, I'll explain in a second why this plus and minus shows up. Then the errors should be small again, 0.002, which is consistent with the Courant factor I've just put in. Okay, so this example used two features that I haven't explained to you yet. Let me talk about those. The first feature was setting initial conditions. So it turns out that the general solution has the form that g of x comma t is equal to one function of only one variable of x minus t plus a second function of variables x plus t. And I'm calling them, and these are arbitrary. I'm calling them R and L because this is a right moving pulse. If I make t larger by say 2, if I also make x larger by the same amount, then the x minus t stays unchanged. So this thing is just, whatever shape it is translating right. Here the x plus t is going to translate things the opposite way. So this is some shape that is translating left. And so if we now have this general shape and we want our pi initial conditions, so we have pi equals, or if we just write down g dot, well, this is now dr dt plus dl tt. And well, r is a function of minus t internally, so this is the same as minus the derivative of r with respect to its one variable. And L, it's a plus t here, and so this is a plus L prime. So G dot is minus R prime plus L prime, whereas, of course, always in our initial conditions, we want to set phi equals the spatial derivative of G, that's the definition of phi. This would be R prime plus L prime. And so you see that there's a different sign showing up here. If I want only a purely left or right going pulse, then say I only have the L pieces. That means for G dot and for phi, I both have to set the same plus L prime. Whereas if I want a right moving pulse, I have only the R pieces. And that means between phi and G dot, I have the sign difference here. And if it's a general shape with both R and L at the same time, well, then you have these types of combination, and whatever it is, it is. And so this is how the G dot initial conditions actually determine information also about the evolution of your system. The second thing I was touching on very briefly is the Courant limit. So it turns out that explicit time steppers, where do I go? All have a maximum time step they can do before they become unstable. If you try bigger time steps, it's not just that you get a less accurate solution, you don't get any solution at all. Let me actually briefly demonstrate. Since I have this up here. So I was using maximum of 8 so far, I believe, 1/8. And so the 1/8 gives me an error of 0.2. Now if I go to 1, 0.2 times 8, that should give me an error of approximately 1. But let's see what's actually happening. The error you get is 500. And as you can see in this top panel, first the solution looks quite quaint. We need to get rid of the last cycle here, otherwise you're not seeing anything. So let's only go into 2 cycles for a change. If I'm only going to 2 cycles, you see that initially this still looks reasonably good, but now we are up at 2 point something already. And 1 cycle more the 2 point something turns into a, this is cool, I haven't tried this, turns into a 10, and one cycle more, the 10 turns into a 500. And if I did one cycle more, the 500 turns into a 50,000. So I think you see the pattern here. This is not getting you anywhere. And where this is coming from is that our explicit time steppers require one to set the time step sufficiently small in order for them to be what's called stable. So explicit time steppers require that you set your time step to be less than a constant times the spatial grid spacing. And this constant is typically order 1, and it depends on the evolution system. It depends on the time stepper. So could be that you could run a different time stepper with somewhat larger time steps. And it also depends on the, what's the third one I want here? The spatial discretization scheme. But it always scales proportional to the time step you have, to the grid spacing you have. And the fundamental, one heuristic reason why this is showing up is that if you had a time step much bigger than delta x, then because information moves with the speed of 1, you would have information propagating across multiple grid points all at once. And if you're propagating too far over too many grid points, then there's just no way to resolve where which information is coming from. And that leads to these quite dramatic blow-ups. So this whole thing goes under the name of Courant limit. Or CFL limit. Courant is the most important name in this business, and the other two are Friedrich and Levy. And so what I'm asking you to do in the problem set this afternoon, and what I've also done here, is to introduce a Courant factor and then to say that delta t is equal to or less than the Courant factor times the smallest grid spacing. And so when I was using 1/8 in here, that means I was choosing a time step where the time step is 1/8 times the grid spacing. The nice thing is, if I do this in terms of Courant factor, if I now change the spatial resolution and the grid spacing changes, what used to be stable will continue to be stable, and I don't run into the case that, great, I have this cool simulation, let me increase resolution. Now it blows up. Oh yeah, I need to reduce the time step. So find time step, reduce, change the number, run again. And the other thing I've shown you, well, actually, two rule of thumbs here. The first one is that CF about 1/4 is usually stable. But if you really know that you can take as big time steps as possible, that you don't care about resolution, then you can experiment, because depending on what evolution system, what time step, or what spatial discretization you happen to be using, it could very well be that you can use a bigger time step. We actually had, as an anecdote, a long time ago, an undergraduate student who had saved us an immense amount of compute time because she wasn't aware of this 1/4. And so she was doing some simulations and was happily using big time steps. And at some point, she talked to us and said, "Oh yeah, I'm doing these simulations. I'm using a Courant factor of 1." Our response was, "Well, no, you shouldn't use this. This doesn't work." But it works. It works just fine. What's your problem? And then we discovered that way by trial and error, and somebody not knowing that you shouldn't be doing that, that for our particular combination of pieces, a Courant factor of 1 was also okay, and that actually had cut down our computing time for this particular project by, well, about a factor of 4. So sometimes these things come in and are important. The other thing to note here is, because our spectral discretization is so accurate, if you do low-order time stepping or even modestly high-order time stepping, then you end up with requiring many time steps, very small Courant factors, as I had illustrated in the problem. So it's always amazing how quickly the time passes. I guess I just have time to introduce 2 more time steppers, and then, Geoffrey, I'm afraid my exposition of characteristic fields and characteristic modes will have to wait until tomorrow. Let me introduce you to the next 2 most obvious and widely used time steppers that are much better than forward Euler. And those are Range-Kutta methods. I'll briefly put on the blackboard Range-Kutta 2 and Range-Kutta 4. I'm putting in RK2 only to illustrate what the idea of Range-Kutta methods are, because once you have seen them all, Range-Kutta 4 is a very good one to use, because it has such a nice combination of simplicity and efficiency and accuracy. Okay, Range-Kutta 2 works quite similar to forward Euler, that we first evaluate an intermediate quantity W1, which is F at time and UK. And so the diagram starts out precisely as over there for forward Euler. Here's again time in units of time steps. Here's the kth time steps. Here's the k plus first time step. Here's the solution U. We have our solution UK. And this first line here gives us the same slope as it did give us for forward Euler. And now comes where the scheme deviates. We next evaluate a new slope, W2, which is also a right-hand side evaluation. But here comes the trick. We are going half a time step forward. Time t plus 1/2. And we are advancing u by 1/2 delta t times our initial slope here. So we're not jumping all the way to up here, but we're only going to 1/2 in the middle. So we're going to this point here next. And at this point, we're now evaluating whatever the slope is at this point. Slope should at least go through the point. So this is the slope W2. Now having W2, we use that one to go to the next time step. UK plus 1 equals UK plus delta T W2. So pictorially, we're moving that line down, that it goes through our initial point. And then over here, this is then UK plus 1. And so what this does is it picks a slope that is more representative of the whole interval covered by the time step instead of just using the initial slope. And that way it actually manages a per order time step error of delta t cubed. And so this method is going to be second order. And so if I do this, I should find that the errors are going to go down, well, polynomially twice as fast as for forward Euler. But of course, the most useful weapon of choice that many people are using is, as I already mentioned, Runge-Kutta 4. And the 4 is going to mean that we now have 4 right-hand side evaluations. And they are split out a little bit differently. So you still start with f of the current time and the current field. Now you play the same game as for Runge-Kutta 2. You go 1/2 delta t into the future, and you go 1/2 in W as well. At that point, life becomes more confusing, and so I won't be doing diagrams anymore. Now you're doing a W3 where you're repeating, where you're still doing the thing in the middle, UK plus 1/2 delta t. And the difference here is that you're using W2. So you're slightly varying the slope where you're evaluating this point up here. And then you're evolving, you're doing a 4th right-hand side evaluation. Actually, at the end of the time step, dk plus delta t, and UK plus delta t times which one? W3. And once you have all these 4 right-hand sides, it turns out you can evaluate the next time step as some weighted sum of all these things there. So UK plus 1 is going to be UK plus 1/6 delta t over 6 W1, 2, W2, 2, W3, W4. Here we go. And I'm missing at least 1 parenthesis. And this thing has an error term of delta t to the 5th. So this one is 4th order. And it's still only 4 lines of code. So it's still very easy to code. And it gives tremendous benefits in terms of accuracy, which makes this a very nice standard weapon of choice. So in terms of my time stepper routine, this is how the RK4 routine looks like, instead that I have been using Ks instead of Ws. You literally can type in these 4 formulas if you have abstracted away the right-hand side calculation into a separate function f. And that's it. And at the end, well, this is just the formula, the last formula I've written down here. So let's try how this works, because it's always startling. Let's switch back to 1/8. And just to remind you, with 1/8, the forward Euler errors are about 0.1 or thereabouts. I've still left for moving one. Doesn't really matter, does it? Okay, let's move to the right moving one. No problem. I think I can handle that if I find the other minus sign. So now it's moving to the right again. The error is 0.4. I think this 0.4 versus 0.2 has basically to do that in this particular case, by pure coincidence, the peak is at a grid point, and beforehand it was between two grid points. But doesn't really matter. Let's switch over to, since I have all three of them, RK2. Let's label it RK2. And so with RK2, we're now down at an error of 0.005. You should be impressed. And with RK4, the error is now at 10 to the minus 6. And we're still only using a Courant factor of 1/8, whereas to get to 10 to the minus 5 with forward Euler, the whole calculation took something like 40 seconds, and I don't remember how many zeros I had to put into the Courant factor. So this really helped a lot. Okay, so now we are 10 to the minus 6. Now let me get ambitious and put another 0 here, making the time step 10 times smaller. So if everything works out, and I haven't tried this before, that should reduce the error by 10 to the 4. So the 10 to the minus 6 should turn into a 10 to the minus 10. 10 to the minus 9. Not too shabby. At that point, I might very well be restricted by the 32 here. And so I would have to increase the number of basis functions. If I go up to 40, then I can still at 5 times 10 to the minus 9. If I go up to 64, let's be ambitious, then we are still at 5 times 10 to the minus 9. So this could very well be the, this didn't really change, did it? Thank you. Okay, so with 40, we're now at 10 to the minus 10 as advertised. And if I make this even smaller, then I guess at some point, again, that the time stepping error will take over. So Range cutter 4 still is not optimal in the sense that I need to go to about 20 times smaller time steps to get the accuracy I need than stability would allow. But it's a number reasonably close to unity, so it's not too bad. Okay. I guess we have 11 o'clock, so let me see whether there's any other questions.
The final where you add the different values. Yeah, that.
Yeah.
It looks like a finite difference. Is there any spectral?
Yes, this looks either like a finite difference stencil or a polynomial. I honestly have no clear answers how these types of things are derived. I can give you a few more trivia about Range cutter methods. So the 3 I have on the blackboard: forward Euler, 1 right-hand side evaluation, first order; Range cutter 2, 2 right-hand side evaluations, second order; Range cutter 4, 4 right-hand side evaluations, fourth order; it turns out this is the highest order where this still works. If you want to go to 5th order or higher, you need to have more right-hand side evaluations as you have your order. And that's one of the reasons why Runge-Kutta 4 is so popular. And I'm bringing this up in the context of your question that, yes, it looks like a finite difference stencil, but whatever intuition you derive from the little things on the blackboard, they actually don't generalize to higher order. So it's not a finite difference stencil at the end of the day. And also these chords here in the middle are getting ever more bizarre with these numbers here becoming ever more complicated as well.
I didn't get how is not a finite system. Answer this question. I didn't get.
It simply isn't. This is a linear combination of all these intermediate results that just happen to give us very nice properties with a high order for the error and a large stability region.
So is there anything like a spectral time step?
The question is are there spectral time steppers? Yes, but they are not particularly widely used. So there's something around called spectral deferred corrections, which basically, here's our time step. It takes the time step, and within the time step, it puts down a set of grid points, Tj, according to some spectral expansion, let it be Chebyshev or Legendre or take your favorite. And then it derives enough data at these time steps to get the time stepping order to be commensurate with the number of stages you have here. It will converge quickly. The downside is, in order to fill all these points here, you have to do some lower order time stepping. So you're first doing some initial time stepping that gives you all these points to a certain order in delta t. And then you're iterating and sweeping through again. And with each sweep, you increase the order by 1. But at the end of the day, you accumulate a fairly large number of right-hand side evaluations. And that's one of the reasons why these methods are not as popular, because they have many right-hand side evaluations. And they are also quite a bit more complicated than 5 lines of code. Thank you very much. I think our next stop is a photo, even before coffee. Thank you.